Hey everyone, welcome back. In this video, we're going to write a minimal startup file for the ATSAM3 X8E from scratch, no libraries. We'll see how the microcontroller boots, how the stack is set, how memory is initialized, and how execution finally reaches the main function. This is exactly what happens on reset inside a Cortex-M microcontroller. Let's get started. First, we include stdn.h, hash include stdn.h. Next, we define the base address of the watchdog timer, hash define wdt underscore base 0x400 e1a50 ul. The watchdog timer is a hardware safety mechanism. It automatically resets the microcontroller if the software stops running correctly. For example, if the code gets stuck in an infinite loop or crashes. During startup, the watchdog timer is enabled by default on the ATSAM3 X8E. If we don't handle it immediately, the microcontroller will reset before our program reaches the main function. In this file, we disable the watchdog to prevent unintended reset during system initialization. Once initialization is complete, the watchdog can be re-enabled later if needed. Here, we define the watchdog mode register, hash define wdt underscore mr inside parentheses asterisk inside parentheses volatile un32 underscore t asterisk and outside inside parentheses wt underscore base plus 0x04u. This register controls how the watchdog operates, including whether it's enabled or disabled, its timeout configuration, and how it triggers a reset. Then we define the watchdog disabled bit, hash define wdt underscore mr underscore wddis underscore pos 15u and hash define wdt underscore mr underscore wddis inside parentheses 1u shifted by the position. Next, we declare several external symbols provided by the linker script, which we'll create in the next video. Extern un32 underscore t underscore si data comma underscore s data comma underscore e data comma underscore s bss comma underscore e bss comma underscore e stack. These symbols are not variables allocated by the compiler. They are addresses defined by the linker. Here, extern means that these symbols are defined somewhere else, not in the C file. Underscore SI data is the load address in flash of the initialized data section. It points to where the initial values of global and static variables are stored before being copied into SRAM. Underscore S data is the start address of the .data section in SRAM, where initialized global and static variables live at runtime. Underscore E data marks the end of the .data section in SRAM and tells us when the copy operation is complete. Underscore SBSS is the start address of the .bss section in SRAM, which contains uninitialized global and static variables. Underscore EBSS marks the end of the .bss section and tells us how much memory must be cleared to 0. Underscore E stack is the top of the stack memory. On reset, the CPU loads this value directly into the stack pointer. Now, we declare the exception handlers. The first one is the reset handler. Void reset underscore handler and it takes void. The reset handler is the first C function executed after a reset. When the microcontroller powers up or resets, the CPU jumps directly to this function. This handler is responsible for initializing memory, disabling the watchdog, preparing the system state, and finally calling the main function. Nothing runs before the reset handler. This function is the real entry point of the program, not main. Next, we declare the default handler, void default _ handler, and it takes void. The default handler is a catch-all exception handler. It is used when an interrupt or exception occurs and no specific handler is provided. Instead of letting the CPU jump to an invalid address or execute random memory, we force execution into a known function. This makes the system safer and much easier to debug because any unexpected interrupt will trap the CPU in a controlled state. Next, we declare the hard fault handler, void hard fault _ handler. It takes void _ attribute _ parenthesis weak comma alias, and inside parenthesis default _ handler. A hard fault occurs when the CPU detects a serious error, such as an invalid memory access or an illegal instruction. _attribute _ is a compiler-specific extension provided by GCC. It allows us to give extra instructions to the compiler about how a function or variable should be treated. In this case, we use it to control how the linker handles this function. The alias attribute makes one symbol point to another symbol. And this part, alias inside parenthesis default handler, tells the linker that if no custom hard fault handler is provided, this handler should be point to default handler. The weak attribute means this symbol has low priority. If we later define another hard fault _ handler with the same name, the linker will automatically use the new one instead. This guarantees that a hard fault is always handled safely, even if we haven't written a specific fault handler yet. Next, we place the interrupt vector table into a dedicated memory section, _ attribute _ inside parenthesis section, and we pass in .isr _ vector. This compiler attribute tells the compiler to place the vector table we define next into .isr _ vector section. The .isr _ vector section contains the interrupt vector table, which holds the initial stack pointer and the addresses of all exception and interrupt handlers. When the microcontroller resets, the CPU immediately looks for this table at a fixed memory location to know where to start execution. By explicitly placing it in .isr _ vector, we make sure the vector table ends up exactly where the hardware expects it. And here is the vector table itself. Const void * vector _ table square brackets equals curly brackets. This is an array of pointers that makes up the vector table. The very first entry is the initial stack pointer, which the CPU loads immediately after reset. Inside parenthesis, void * and outside reference _ stack. The next entry is the reset handler, reset _ handler. The next entry corresponds to the NMI or non-maskable interrupt exception. On a microcontroller, NMIs are reserved for critical system events that must be handled immediately and cannot be masked or ignored. Here, we point the NMI entry in the vector table to the hard fault handler for simplicity. And here we say hard fault _ handler. And the next one is the hard fault handler itself. Unused vector entries are left as 0, and here we say 0. If they are ever invoked, the CPU will enter a fault because there is no valid handler. When an exception or interrupt occurs, the CPU uses the corresponding index in this table to jump directly to the correct handler. Next, we implement the reset handler function. Void reset underscore handler, and it takes void. The first thing we do inside the reset handler is disable the watchdog timer to prevent unexpected reset during startup. wdt underscore mr equals wdt underscore mr underscore wddis. Next, we set up a pointer to the initial data values stored in flash. Const un32 underscore t asterisk src equals reference underscore si data. We stored the underscore si data address in a pointer called src, which we'll use to copy its values into RAM. This step is required because the CPU starts executing from flash, but initialized variables must live in RAM during runtime. Then we create the destination pointer in RAM, uint32 underscore t asterisk dst equals reference underscore s data. This is where initialized global and static variables will live during program execution. We stored the underscore s data address in the dst pointer, which will receive the data copied from flash. Using both the source and destination pointers, we can copy initialized data from flash into RAM before main runs. Okay, let's copy the initialized data from flash into RAM. Well, inside parentheses, dst less than reference underscore e data, and inside the loop we say asterisk dst plus plus equals asterisk src plus plus. Next, we clear the .bss section in RAM. dst equals reference underscore spss while dst less than reference underscore ebss, and inside the loop asterisk dst plus plus equals 0. The .bss section contains global and static variables that are not explicitly initialized. By C standard, these variables must start with a value of 0. And we transfer control to the main function, extern int main, and it takes void, and we call the main function main. At this point, all low-level initialization is complete and the system is ready to run application code. And finally, we add an infinite loop, while 1. This is a safety measure. If something goes wrong in our application and main ever returns, the CPU won't execute random memory. It keeps the system in a controlled state until a reset occurs. And at the end, we implement the default handler function, void default underscore handler, and it takes void. And inside the default handler, we add an infinite loop for safety, while 1. That's it for our minimal startup file for the ATSAM3X8E. In the next video, we'll dive into the linker script and show you how symbols like underscore sdata, underscore ebss, and underscore estack are defined and mapped in memory. And we'll also explore how to place sections like .txt, .data, and .bss exactly where the hardware expects them. Make sure to follow along because understanding the linker is key to controlling the memory layout of your embedded application. Thanks for watching, and I'll see you in the next video.